Picture this, a place in the cosmos so vast, so unimaginably heavy, that it bends the fabric of space-time around it like a bowling ball on a trampoline. The Perseus Cluster isn't just another speck in the night sky. It's a monster of the universe, weighing in with the mass of quadrillions of suns. But here's the twist: the deeper we look, the more it refuses to make sense. Galaxies zooming at impossible speeds, ghostly threads of gas glowing with no clear source, even a bizarre, persistent hum reverberating through the void. These aren't just oddities, they're cosmic crimes against everything we think we know about physics. In this video, we're diving into 25 of the most baffling mysteries lurking in the Perseus Cluster, phenomena so strange they've left scientists scratching their heads for decades. From missing matter to rogue black holes, each one challenges the rules of the universe as we know them. Buckle up, because by the end, you'll never look at the night sky the same way again. And trust me, some of these enigmas will make you question whether we've ever truly understood how space works. Now, let's peel back the layers of the first jaw-dropping mystery, the missing mass problem. Here's the thing: when scientists calculate how much stuff the Perseus Cluster should have based on its gravity, the numbers just don't add up. It's like stepping on a scale and watching it show half your weight. Something's clearly off. The cluster's gravitational pull suggests there's way more matter here than what we can actually see with telescopes. Stars, gas, dust, they all account for just a fraction of what the math demands. So where's the rest? This isn't just a Perseus Cluster quirk. It's a cosmic riddle that pops up everywhere we look, and the leading suspect, dark matter. Imagine an invisible skeleton holding the universe together. We can't see it, touch it, or detect it directly, but its gravitational fingerprints are everywhere. In the Perseus Cluster, dark matter would explain why galaxies orbit at breakneck speeds without flying apart. Without it, the laws of physics as we know them would crumble. But here's where it gets even weirder. If dark matter is real, why can't we catch it in the act? Countless experiments have hunted for particles that could make up this elusive substance, from deep underground labs to space-based detectors. Yet, decades later, we've got nothing definitive. Some theories suggest dark matter might interact with itself in ways we don't yet understand, or that it's not a single particle but a whole shadowy sector of physics. Others argue we might need to rewrite gravity itself. That's right, alternative ideas like modified Newtonian dynamics or MUND propose that gravity behaves differently on cosmic scales. Instead of invoking invisible matter, maybe Einstein's equations need a tweak. But here's the catch: while MUND can explain some galaxy rotations, it stumbles when faced with the sheer gravitational might of clusters like Perseus. The math gets messy and the gaps remain, so the mystery stands. Either the universe is stuffed with a ghostly substance we can't perceive, or our grasp of gravity, the force we thought we knew best, is fundamentally flawed. For now, the Perseus Cluster keeps its secrets locked tight, leaving scientists racing to solve one of astronomy's greatest puzzles. And this is just the first enigma on our list. Moving beyond dark matter, let's wrestle with another fascinating idea. What if the problem isn't missing matter at all, but our understanding of gravity itself? Enter modified Newtonian dynamics, or MUND. This bold framework suggests that gravity doesn't weaken as quickly over vast distances as Newton and Einstein predicted. Instead, it tweaks the rules just enough to explain why galaxies rotate faster than expected without invoking invisible dark matter. Picture gravity as a car engine. MUND argues we've been misreading the manual, and with a few adjustments, the cosmic math might finally add up. At first glance, MUND works surprisingly well for individual galaxies. Their rotation curves, the speeds of stars at different distances from the center, fall neatly into place without dark matter's helping hand. But the Perseus Cluster throws a wrench into this elegant solution. Clusters are gravity's ultimate stress test, where the pull of countless galaxies and hot gas creates a gravitational monster. Here, MUND struggles. Even with its modified rules, the numbers still come up short. The cluster's sheer mass requires something extra, whether that's unseen particles or a deeper flaw in our gravity models. Critics point out another headache: the cosmic web. Dark matter elegantly explains how the universe's large-scale structure, filaments of galaxies spanning billions of light-years, formed after the Big Bang. MUND, meanwhile, lacks a robust cosmic recipe. Computer simulations of the early universe built on dark matter align beautifully with what we observe today. Without it, the web's intricate architecture becomes harder to explain. Yet MUND isn't bowing out quietly. Recent refinements, like relativistic versions (TVS), attempt to bridge the gap between galaxy-scale successes and cluster-scale failures. Some theorists even speculate that gravity's behavior might change in extreme environments, like the heart of galaxy clusters, but these ideas remain contentious. The biggest hurdle: gravitational waves. When LIGO detected ripples in spacetime from colliding black holes, their behavior matched Einstein's predictions flawlessly, no modifications needed. If gravity bends the rules, it's doing so invisibly. So where does this leave us? Dark matter has the edge for now, but the debate is alive and kicking. The Perseus Cluster, with its gravitational puzzles, stands as a battleground for these competing visions of the cosmos. Whether the answer lies in unseen particles, rewritten physics, or something even stranger, one thing's certain: the universe loves keeping us guessing. And just wait until you hear about the next mystery lurking in this cluster's depths. Now, let's turn our attention to something equally puzzling but far more visible, or at least detectable. The Perseus Cluster is wrapped in an enormous, ghostly cloak of radio waves, stretching millions of light-years across. This so-called radio halo isn't just faint background noise, it's a colossal signature of energy, and its origins have astronomers scratching their heads. Imagine tuning an old radio between stations and hearing static. That's essentially what this halo is, but on a cosmic scale. It's not coming from any single galaxy or black hole. Instead, it's a diffuse, all-encompassing emission that blankets the entire cluster. At first glance, you might think it's just the result of cosmic rays zipping through magnetic fields, which is how similar radio emissions are generated elsewhere in the universe. But here's the twist. The Perseus Cluster's halo is far more energetic and widespread than those models can explain. The leading theory suggests this radio halo is linked to the cluster's violent past. When galaxy clusters collide, the shockwaves can accelerate particles to nearly the speed of light, creating a sea of high-energy electrons. These electrons then spiral around magnetic fields, producing the radio waves we detect. But in Perseus, there's a problem: the halo is too bright and too uniform. If it were purely from past collisions or ongoing turbulence in the cluster's gas, we'd expect patchy, uneven emission. Instead, it's eerily smooth, as if something else is powering it evenly across the entire region. Another puzzle is the halo's sheer size. For conventional cosmic ray explanations to hold, the magnetic fields in the Perseus cluster would need to be improbably strong and perfectly distributed. Observations, however, show the fields are patchy and weaker than required. This mismatch has led some researchers to explore wilder possibilities, like dark matter particles annihilating each other and releasing energy as they do. While intriguing, there's no direct evidence yet to support this idea, leaving the halo's true nature wide open. What makes this mystery even more compelling is that similar radio halos have been spotted in other clusters, yet none are quite like Perseus. Its halo is brighter, more extensive, and more enigmatic. Some scientists argue it could be a sign of unseen physics, a cosmic phenomenon we haven't even theorized yet. Others suggest it's a combination of multiple processes, each amplifying the other in ways we don't fully understand. one thing's certain: the Perseus Cluster's radio halo is more than just cosmic static. It's a fingerprint of something far more profound, challenging our assumptions about particle acceleration, magnetic fields, and even the invisible scaffolding of the universe itself. And as we'll soon see, this isn't the only strange signal coming from this cluster's depths. Now, shifting our gaze even deeper into the unknown, let's explore one of the most tantalizing possibilities behind the Perseus Cluster's radio halo: its potential connection to dark matter. This invisible substance makes up roughly 85% of the universe's mass, yet we've never directly observed it. Could this mysterious halo be our first glimpse of dark matter's hidden interactions? The idea goes like this: if dark matter particles collide and annihilate one another, they could release bursts of energy, including high-energy electrons and positrons. These particles would then spiral around magnetic fields, producing the very radio waves we detect. It's an elegant solution on paper, but here's where things get tricky. For dark matter annihilation to explain the halo's smooth, uniform glow, the particles would need to be distributed perfectly evenly across the entire cluster, something we've never seen in nature. Some theories suggest a specific type of dark matter particle, like the hypothetical WIMP, weakly interacting massive particles, could be responsible. WIMP are among the leading candidates for dark matter, and if they exist, their collisions could generate the right amount of energy to power the radio halo. But there's a catch: current models predict these annihilations would also produce gamma rays, which we haven't detected in sufficient quantities around Perseus. Another twist comes from actions, another speculative dark matter particle. Unlike WIMP, actions could convert into photons in the presence of strong magnetic fields, potentially creating the radio emission we see. Yet again, though, the math doesn't quite add up. The required action density and magnetic field strengths don't match our observations, leaving this theory on shaky ground. What's fascinating is that even if dark matter isn't the sole culprit, it might still play a supporting role. Some researchers propose a hybrid scenario where cosmic rays accelerated by cluster collisions interact with dark matter particles, boosting the radio signal beyond what conventional physics predicts. This would explain both the halo's brightness and its strange uniformity. Of course, not everyone is convinced. Skeptics argue that the halo could still be explained by extreme versions of known astrophysical processes, like turbulence in the cluster's gas or unresolved outbursts from active galaxies. But until we find definitive proof, perhaps from next-generation telescopes or particle detectors, the dark matter connection remains one of the most compelling, if elusive, explanations. Whether it's dark matter or something even stranger, the Perseus Cluster's radio halo is forcing us to rethink the boundaries of physics. And as we'll see next, this isn't the only enigma lurking in the cluster's depths. Some of its most bizarre features are just waiting to be unraveled. Now, let's turn our attention to something just as puzzling but far more explosive: the bizarre X-ray cavities lurking within the Perseus Cluster. These aren't your ordinary cosmic voids. Imagine gigantic bubbles, each spanning tens of thousands of light-years, carved out of the cluster's scorching hot gas. They're invisible in optical light, but in X-rays, they glow like ghostly fingerprints, revealing the violent handiwork of the cluster's supermassive black hole. At the heart of the Perseus Cluster lies NGC 1275, a galaxy hosting one of the most active black holes we've ever observed. As this monster feasts on surrounding matter, it doesn't just swallow material quietly, it belches out enormous jets of energy, punching through the cluster's gas and inflating these colossal cavities. Think of it like blowing bubbles in a thick syrup, except these bubbles are filled with ultra-fast particles and magnetic fields, pushing aside the million-degree plasma around them. Here's where the mystery deepens. According to our models, the energy required to create these cavities should match the output of the black hole's jets. But when astronomers crunched the numbers, something was off. The energy distribution doesn't line up. The cavities are far more energetic than the jets alone can explain, as if there's an invisible force amplifying their power. Some suggest that turbulence in the cluster's gas might be transferring extra energy into the bubbles, like ocean waves feeding into a whirlpool. Others propose that the black hole's outbursts are more chaotic than we thought, with hidden bursts of activity we haven't yet detected. Then there's the strangeness of the cavity's shapes. They're not perfect spheres. Some are elongated, others asymmetrical, as if something is warping them from the inside. One theory points to the cluster's own magnetic fields, twisting and stretching the bubbles over time. Another idea is that older cavities, left over from past black hole eruptions, are colliding with newer ones, creating these distorted forms. But without a clear way to track their evolution, these explanations remain speculative. What's truly baffling is how long these cavities persist. In most environments, such structures would dissipate within millions of years, but in Perseus, they linger for much longer, defying the laws of fluid dynamics. It's as if the cluster's gas is thicker or more elastic than we've accounted for, or perhaps some unseen mechanism is constantly replenishing their energy. The implications are huge. If we can unravel how these cavities form and endure, we might unlock secrets about how black holes shape entire clusters, and by extension, the universe itself. But for now, the Perseus Cluster's X-ray cavities stand as a stark reminder that even our best theories can't fully capture the chaos of the cosmos. And as we'll soon see, this isn't the only enigma where the cluster's reality outstrips our predictions. But the story doesn't end with the X-ray cavities themselves. What's even more fascinating is what they reveal, or rather, what they hide about the delicate dance between supermassive black holes and their surroundings. This is where the mystery of black hole feedback comes into play, a process we thought we understood until the Perseus Cluster threw us a cosmic curveball. Black hole feedback is essentially the universe's way of balancing the books. When a supermassive black hole devours matter, it doesn't just hoard the energy, it releases some back into its environment through those powerful jets, heating up the surrounding gas and preventing it from cooling too much. Without this feedback, galaxies would grow uncontrollably, stars would form at breakneck speeds, and cosmic structures would look nothing like what we see today. In theory, it's a beautifully self-regulating system. But the Perseus Cluster's cavities are exposing cracks in that theory. For starters, the sheer scale of energy mismatch is staggering. Those cavities we talked about earlier, they're not just leftovers from a black hole's lunch, they're evidence of a system wildly out of sync. The energy pumped into them should, according to our models, suppress star formation across the cluster by keeping the gas too hot to collapse. Yet in Perseus, we see galaxies forming stars at rates that defy this logic. It's as if the black hole's feedback is either leaking energy or missing its target entirely. Some astronomers suspect the jets might be channeling energy into unexpected places, like stirring up turbulence in the gas rather than evenly heating it. Others wonder if the cluster's complex magnetic fields are redirecting the energy, creating pockets where gas can still cool and form stars. Then there's the timing problem. Black hole outbursts are supposed to be sporadic, with long quiet periods between violent eruptions, but the cavities in Perseus suggest a rhythm we don't fully grasp. Some appear to overlap or sit nestled inside one another, hinting at repeated outbursts on timescales we can't yet measure. If the black hole is erupting more frequently or more unpredictably than we thought, it could mean our entire framework for feedback needs recalibrating. Perhaps the most puzzling clue comes from the cavity's longevity. If black hole feedback is as efficient as we believe, these structures shouldn't stick around for hundreds of millions of years. Yet they do, acting like cosmic insulation that traps energy rather than dispersing it. One bold idea is that the cluster's dark matter halo might be playing a role, its gravity somehow stretching and preserving the cavities like an invisible hand shaping clay. What's clear is this: the Perseus Cluster isn't just challenging what we know about black hole feedback, it's showing us how much we've oversimplified the chaos of the cosmos. Every assumption, from how energy propagates to how galaxies evolve in clusters, is up for debate. And as we'll see next, this isn't the only place where the cluster's cold fronts rewrite the rules of astrophysics. Now, let's shift our focus to something that defies the very laws of fluid dynamics: the enigmatic cold fronts of the Perseus Cluster. Picture this: vast waves of gas, some stretching over 50,000 light-years, where temperatures drop sharply, like cosmic ocean currents frozen in time. These aren't just minor fluctuations, they're some of the most pronounced temperature gradients ever observed in space. And here's the kicker: they've remained stable for billions of years, a longevity that baffles scientists because, according to everything we know about how gases behave, they should have dissipated eons ago. So, what's keeping these cold fronts intact? Under normal circumstances, gases in space, especially in the violent environment of a galaxy cluster, should mix and smooth out over time due to turbulence and collisions. Think of it like pouring cold milk into hot coffee. Eventually, it all blends together. But in Perseus, the cold gas refuses to mix. It's as if an invisible barrier is preserving these sharp boundaries, and that's where the mystery deepens. One leading theory points to magnetic fields. We've long known that galaxy clusters are threaded with magnetic fields, but in Perseus, their strength and structure might be extraordinary. These fields could act like cosmic insulation, wrapping around the cold gas and preventing it from eroding into the surrounding hot medium. Imagine a bubble wrapped in a magnetic sheath, holding its shape against the chaotic swirl of the cluster. Recent observations hint that these fields are far more organized than we thought, potentially forming intricate layers that shield the cold fronts from disruption. But magnetism alone might not explain everything. Another piece of the puzzle involves the cluster's turbulent history. The Perseus Cluster didn't form peacefully. It grew through violent mergers with smaller galaxy groups, collisions that would have sent shockwaves rippling through its gas. Some researchers propose that these ancient shocks compressed the gas into dense, cold slabs, and the sheer inertia of these structures has allowed them to persist. It's like tossing a boulder into a river. The water flows around it, but the boulder stays put. Yet even this explanation has cracks. Simulations show that without some additional stabilizing force, these cold fronts should have frayed at the edges long ago. That's why some scientists are now considering dark matter's role. Could the cluster's invisible halo of dark matter be subtly shaping the gas dynamics, its gravity acting like a scaffold that reinforces the cold fronts? It's a tantalizing idea, but one that's notoriously hard to test given dark matter's elusive nature. What makes these cold fronts particularly thrilling is how they challenge our understanding of fundamental physics. They're not just cosmic curiosities, they're natural laboratories forcing us to rethink how energy, magnetism, and gravity interact on scales we can barely simulate. And as we'll soon see when we peer even closer, the Perseus Cluster has another surprise in store: ghostly filaments that defy explanation. Now, as we peel back another layer of this cosmic mystery, let's zoom in on the magnetic fields of the Perseus Cluster, forces so peculiar they're rewriting the rules of astrophysics. These aren't your average magnetic fields, they're cosmic powerhouses up to 10 times stronger than predicted, and they're playing a game of keep away with those baffling cold fronts we just explored. Here's the problem: standard models assume galaxy clusters have weak, disorganized magnetic fields like tangled spaghetti. But Perseus laughs in the face of those assumptions. Observations from radio telescopes reveal fields so intense and structured, they resemble vast, invisible spiderwebs draped across the cluster. These fields aren't just present, they're actively shaping the gas around them. Think of them as cosmic force fields, channeling and containing the cluster's turbulent energy in ways we never anticipated. So how does this defy expectations? For starters, magnetism on this scale shouldn't be so coherent. When galaxies collide, a common event in clusters, their magnetic fields should shred into chaos. But in Perseus, the fields appear oddly resilient, even reinforcing cold fronts like an invisible glue. Some researchers suggest these fields are frozen into the gas, a phenomenon where charged particles lock magnetic lines in place as they move. It's like stirring honey with a magnet inside. The honey flows, but the magnetic pattern holds firm. This could explain why the cold fronts stay crisp despite the cluster's violence. But there's a twist. These magnetic fields might also be amplifying themselves. Turbulence in the cluster's gas could act like a dynamo, spinning and stretching magnetic lines until they grow stronger, a process called the small-scale dynamo effect. Imagine a cosmic generator churning out magnetic energy faster than it can dissipate. If true, Perseus isn't just preserving magnetic fields, it's manufacturing them. Yet even this doesn't fully solve the puzzle. These ultra-strong fields should generate heat as they interact with the gas, yet the cold fronts remain well cold. That's led to wilder theories like magnetic shadows, where fields block thermal energy from reaching certain regions. Picture a giant cosmic umbrella shielding patches of gas from the cluster's scorching heat. What's truly groundbreaking is how these anomalies force us to rethink galaxy clusters altogether. They're not just blobs of hot gas, they're electrified, magnetized labyrinths where invisible forces call the shots. And as we'll see next, when we follow these magnetic threads deeper, they lead us to something even eerier, the ghostly filaments floating through the cluster like cosmic cobwebs. Now, let's turn our attention to one of the most haunting mysteries of the Perseus Cluster, the ghost filaments. Picture these as faint, glowing threads of ionized gas, weaving through the cluster like cosmic cobwebs, stretching for tens of thousands of light years. Unlike the violent chaos of colliding galaxies or the searing heat of the cluster's gas, these filaments are eerily delicate, almost serene, but don't let their fragile appearance fool you. These structures are at the center of a heated debate among astronomers, challenging our understanding of how energy moves through the universe. The first question is simple: how do these filaments even exist? The Perseus Cluster is a turbulent place where galaxies smash together and supermassive black holes blast out jets of energy. In such a hostile environment, you'd expect these wispy threads to be torn apart instantly. Yet they persist, glowing faintly in radio and optical wavelengths. One leading theory suggests they're the fallout of ancient collisions, remnants of gas ripped from galaxies during violent encounters, left to cool and condense over billions of years. Imagine a cosmic crime scene where these filaments are the faint fingerprints of long-forgotten galactic smash-ups. But there's another, far more exotic possibility. Some researchers argue these filaments might be cosmic energy highways, channeling particles and magnetic fields across the cluster. Here's where it gets fascinating. The supermassive black hole at the heart of the Perseus Cluster, NGC 1275, is known to shoot out jets of high-energy particles. These jets could be interacting with the surrounding gas, creating shock waves that compress and ionize it, sculpting the filaments we see today. It's like blowing smoke through a spiderweb. The energy flow shapes the structure. Then there's the role of cosmic rays. These high-energy particles, zipping through space at near-light speeds, might be lighting up the filaments like neon signs. As cosmic rays collide with the gas, they could excite its atoms, causing it to glow. This would make the filaments not just passive relics, but active, dynamic features, buzzing with invisible energy. But the real puzzle is their durability. How do these filaments avoid dissolving into the surrounding hot gas? One clue lies in the magnetic fields we just explored. Those spiderweb-like fields might be acting as a scaffold, holding the filaments together against the cluster's turmoil. It's as if the universe has woven its own invisible net to cradle these eerie structures. And here's the kicker. If these filaments are indeed tied to cosmic rays or black hole activity, They could be a hidden part of the cluster's energy budget, a way for the Perseus cluster to redistribute heat and particles in ways our models don't yet account for. That would mean we're missing a key piece of the puzzle in understanding how galaxy clusters evolve. So what's next? Astronomers are racing to untangle these ghostly threads, using ever more sensitive telescopes to probe their secrets. Each new observation peels back another layer, revealing whether they're cosmic fossils, energy conduits, or something even stranger. One thing's certain: these filaments are more than just pretty light shows. They're clues to forces shaping the universe in ways we're only beginning to grasp. And as we'll soon see when we shift our gaze to the cluster's central galaxy, NGC 1275, the mysteries only deepen. Now, let's take a closer look at the cosmic rays that might be lighting up these ghostly filaments like a celestial neon sign. Cosmic rays are ultra-fast particles, mostly protons and atomic nuclei, racing through space at nearly the speed of light. When they collide with the thin gas in these filaments, they can energize it, causing it to glow in wavelengths we can detect. Think of it like a high-energy car crash where the impact releases bursts of light, revealing paths we'd otherwise never see. But here's the twist: cosmic rays aren't just passive bystanders. They could be actively shaping these filaments, even helping them survive the chaos of the Perseus cluster. The magnetic fields we mentioned earlier might act like cosmic guardrails, trapping and funneling these particles along the filaments. This creates a feedback loop. The cosmic rays energize the gas, and the magnetic fields keep everything in place, like an invisible highway system guiding traffic through a storm. Now, shift your perspective for a moment. What if these filaments aren't just relics of past black hole outbursts, but ongoing energy channels? The supermassive black hole at the cluster's center, NGC 1275, is a known powerhouse blasting out jets of particles and radiation. Some scientists propose that these jets could inject fresh cosmic rays into the filaments, constantly re-energizing them. It's like a cosmic power grid, with the black hole as the generator and the filaments as transmission lines carrying energy across the cluster. But there's another layer to this puzzle. If cosmic rays are indeed playing a major role, why do we only see these filaments in certain parts of the cluster? One possibility is that the environment has to be just right, dense enough to trap the particles, but not so turbulent that it tears them apart. It's a delicate balance, like walking a tightrope in a hurricane. And that might explain why these structures are so rare and mysterious. So where does this leave us? If cosmic rays are the key, then these filaments could be more than just fossils. They might be active players in the cluster's ecosystem, redistributing energy in ways we don't fully understand. That would mean our models of galaxy clusters are missing a critical piece of the puzzle, one that could change how we think about the life cycles of these colossal structures. As we peel back the layers, one thing becomes clear: the ghost filaments of the Perseus cluster are more than meets the eye. Whether they're cosmic ray superhighways, black hole relics, or something even stranger, they're forcing us to rethink the invisible forces shaping our universe. And with every new discovery, we're one step closer to unraveling their secrets. Now, let's turn our attention to the heart of the Perseus cluster, where the central galaxy, NGC 1275, defies expectations by glowing far brighter than it should. This isn't just a flicker of excess light. It's a full-blown cosmic spotlight radiating intense energy in radio and X-ray wavelengths. Normally, galaxies like this would blend into the background of the cluster, but NGC 1275 stands out like a beacon, and that raises a big question: what's powering this extraordinary brightness? At the center of this mystery lies a supermassive black hole, one of the most massive known in the universe. But here's the catch: black holes are supposed to be dark, right? Not this one. Instead of lurking in the shadows, NGC 1275 black hole is incredibly active, spewing out jets of high-energy particles and radiation at nearly the speed of light. These jets collide with the surrounding gas, heating it to extreme temperatures and causing it to glow brightly in X-rays. Meanwhile, the black hole's magnetic fields accelerate particles to such high energies that they emit powerful radio waves, creating a dual-spectrum light show that astronomers can't ignore. But why is this happening here and not in other similar galaxies? One theory suggests that NGC 1275 is feasting on an unusually large amount of surrounding material. As gas and stars spiral into the black hole's gravitational pull, the friction and compression generate immense heat and energy. It's like throwing logs into a fire. The more you add, the brighter it burns. But even that doesn't fully explain the sheer intensity of the emissions. Some researchers propose that the black hole might be in a special phase of activity, perhaps triggered by a recent merger with another galaxy, funneling even more material into its grasp. Then there's the puzzle of the jet interactions. Normally, black hole jets punch through galaxy clusters in relatively straight lines, but in NGC 1275, they seem to be twisting and contorting as if fighting against unseen forces. This could mean the surrounding gas is denser than expected, or that magnetic fields are bending the jets in unexpected ways. Either scenario would make this system unique, challenging our understanding of how black holes influence their environments. What makes NGC 1275 even more intriguing is that its brightness isn't constant. Observations show fluctuations in its X-ray and radio output, hinting at turbulent activity near the black hole. Imagine a stormy ocean where waves rise and crash unpredictably. That's what might be happening in the chaotic environment around this cosmic powerhouse. These variations could be clues about how black holes cycle through periods of feeding and quiescence, but we're still piecing together the full story. So, what does this mean for our understanding of galaxy clusters? NGC 1275 Overbright nature suggests that supermassive black holes might play a far more dynamic role in shaping their surroundings than we once thought. Instead of being passive anchors at the centers of galaxies, they could be active architects, redistributing energy and influencing the evolution of entire clusters. And if that's true, then NGC 1275 isn't just an oddity, it's a preview of the hidden forces governing the universe's largest structures. As we continue to study this luminous enigma, one thing is certain. The more we learn about NGC 1275, the more questions it raises. Whether it's the black hole's insatiable appetite, the strange behavior of its jets, or the unpredictable flickers of its light, this galaxy is rewriting the rules of cosmic physics. And with each new discovery, we get closer to unraveling the secrets of how the most extreme objects in the universe shape the world around them. But the intrigue doesn't stop there. Let's zoom in on those high-speed jets blasting from NGC 1275 supermassive black hole. These aren't just straight, predictable beams. They're bending, twisting, and even flaring in ways that defy our expectations. The jets, made up of particles racing at nearly the speed of light, should punch through the surrounding gas like a laser through fog. Instead, they're dancing as though the cluster itself is pushing back. So, what's causing this cosmic tug of war? One possibility is the sheer density of the Perseus Cluster's gas. Picture trying to swim through molasses. The thicker the liquid, the harder it is to move. The jets might be plowing into pockets of ultra-dense gas, forcing them to slow down and curve. Another clue comes from magnetic fields. These invisible forces could be acting like cosmic railings, guiding the jets into spirals or even splitting them into branches. Normally, we'd expect magnetic fields to weaken over such vast distances, but in NGC 1275, they seem to stay surprisingly strong, adding another layer of mystery. Then there's the shock factor. When these jets slam into the cluster's gas, they create colossal shock waves. Think sonic booms, but on a galactic scale. These shocks heat the gas to millions of degrees, making it glow in X-rays. But here's the twist: some of these shock fronts aren't where they should be. Instead of forming neat rings around the jets, they're asymmetrical, like splatters from a messy collision. That suggests the jets might be interacting with turbulence in the cluster, or even with older, forgotten outbursts from the black hole's past. It's like listening to an echo in a cavern, only to realize the sound is bouncing off walls you didn't know were there. What's really mind-bending is the energy balance. The jets pour out enough power to reshape entire galaxies, yet the cluster's gas doesn't scatter as predicted. Some simulations show the energy should dissipate quickly, leaving the gas calm. Instead, it's like stirring a pot that never stops boiling. This mismatch hints at hidden processes. Perhaps the jets are injecting energy in cycles, or the gas has properties we haven't accounted for. Either way, it's a reminder that even our best models can't fully capture the chaos of a live cosmic event. And just when you think it can't get stranger, there's the mystery of the knots. Along the jets, astronomers have spotted bright clumps of material that flare and fade unpredictably. These knots might be signs of instabilities in the jet's flow, or they could be evidence of material falling back into the jet after a collision. Imagine a fire hose spraying water, only to have some of the droplets curve back midair. It defies normal physics. Yet in NGC 1275, it's happening across light years. All this chaos has big implications. If jets can bend and rebound like this, they might redistribute energy across the cluster in ways we've never imagined. Instead of simply heating the gas, they could be stirring it, creating pockets of turbulence that last for eons. That would mean black holes don't just influence their immediate surroundings, they're puppeteers of the entire cosmic web. As we piece together these interactions, one truth becomes clear. NGC 1275 jets aren't just cosmic fireworks. They're a laboratory for the most extreme physics, challenging us to rethink how energy flows through the universe. And with every new observation, we're not just solving puzzles, we're uncovering rules we didn't know existed. Now, let's shift our gaze to something even more elusive, a galaxy that seems to defy the very definition of a galaxy. Nestled within the Perseus Cluster, astronomers have stumbled upon what they call a dark galaxy, a ghostly structure that appears to have almost no stars at all. Imagine a cityscape with towering skyscrapers but no lights in the windows, no signs of life. That's the eerie reality of this celestial oddity. Most galaxies, like our Milky Way, are dazzling collections of stars, gas, and dust held together by gravity. But this dark galaxy challenges that blueprint. Observations suggest it's dominated by something invisible, dark matter. In fact, the sheer gravitational pull of this object implies it's packed with dark matter, yet it emits almost no light. It's as if the universe built a galaxy and forgot to turn on the lights. How does something like this even form? One theory points to a cosmic misfire. During the early universe, dense clumps of dark matter may have pulled in gas to form stars, but for some reason this one failed. Perhaps the gas was stripped away by the violent environment of the cluster, or it was simply too diffuse to ignite star birth. Another possibility is that this galaxy is a failed dwarf, a small structure that never gathered enough material to shine brightly. But the real puzzle is how we even detected it. Without stars, dark galaxies are nearly invisible. Astronomers rely on indirect methods, like studying the way its gravity distorts light from background objects, a technique called gravitational lensing. In rare cases, faint radio waves or hydrogen gas emissions might betray its presence. Yet even these clues are whisper-thin, leaving scientists to wonder how many more of these shadowy galaxies are lurking undetected. The existence of dark galaxies could rewrite our understanding of cosmic evolution. If they're common, they might represent a missing link in galaxy formation, structures that never quite made it to full starlit glory. They could also be the purest reservoirs of dark matter, offering a unique laboratory to study this mysterious substance. After all, in a normal galaxy, dark matter is mixed with stars and gas, making it hard to isolate. But here, it might be the only ingredient, yet skepticism lingers. Some researchers argue that what we're seeing isn't a dark galaxy at all, but a tidal debris field, a shredded remnant of a galaxy torn apart by the cluster's gravity. Others suggest it could be a misalignment of data, a trick of observation. But if confirmed, this dark galaxy forces us to ask, is the universe hiding an entire population of invisible galaxies? And if so, what does that mean for our cosmic senses? One thing is certain, the Perseus Cluster continues to serve up mysteries that challenge the limits of our knowledge. From bending jets to starless galaxies, it's a reminder that the universe is far stranger and far more inventive than we ever imagined. And as we peer deeper into its shadows, who knows what other secrets await discovery? Now, let's tackle the challenge of uncovering these cosmic ghosts, because finding a dark galaxy isn't just like searching for a needle in a haystack. It's like searching for a needle that doesn't glow, reflect, or emit anything recognizable in a haystack the size of the universe. The very nature of these starless structures makes them almost invisible to traditional telescopes. After all, how do you spot something that doesn't shine? Most galaxies announce their presence with bright stars, glowing gas, or blazing black holes. But dark galaxies, they're the ultimate cosmic ninjas, slipping through observations undetected unless they give themselves away through subtle gravitational effects. One of the few ways astronomers can catch them is by watching how they warp the light of background galaxies, a phenomenon called gravitational lensing. Think of it as spotting a hidden object by the way it bends the light around it, like an invisible lens in space. Even then, the distortion has to be just right, and the dark galaxy's mass must be significant enough to leave a detectable fingerprint. Another clue comes from faint whispers of hydrogen gas. Some dark galaxies may harbor trace amounts of this primordial fuel, emitting radio waves at specific frequencies. Instruments like the Arecibo Observatory, before its collapse, and today's powerful radio telescopes like the Square Kilometre Array have scanned the skies for these elusive signals. But here's the catch: the gas emissions are so faint that they're often drowned out by the cosmic noise of the universe. It's like trying to hear a whisper in a hurricane. And then there's the problem of misidentification. What looks like a dark galaxy could actually be a tidal tail, a stream of debris ripped from a visible galaxy during a collision. The Perseus Cluster, with its violent mergers and gravitational turmoil, is full of these chaotic remnants. Distinguishing a true dark galaxy from these cosmic leftovers requires painstaking analysis, and even then, doubts linger. But why does any of this matter? Because if dark galaxies are real and plentiful, they could rewrite the story of how galaxies evolve. Current models suggest that dark matter clumps first, then pulls in gas to form stars. But if entire galaxies can exist without stars, it hints that the universe might have more paths to building structures than we thought. These shadowy objects could be cosmic dead ends, places where galaxy formation stalled, or they might be hidden cradles, quietly hoarding gas until the right conditions spark star birth. Their existence also raises bigger questions. Could dark galaxies be the missing repositories of the universe's lost baryonic matter, the ordinary atoms we can't account for? Or are they proof that dark matter behaves in ways we haven't yet imagined? Every undetected dark galaxy is a blank space in our cosmic map, a reminder that what we don't know might far outweigh what we do. As technology advances, so does our hunt for these invisible giants. Upcoming telescopes like the Vera C. Rubin Observatory will scan the skies with unprecedented depth, potentially revealing more of these enigmatic structures. But for now, the dark galaxies of the Perseus Cluster remain shadowy puzzles, both a challenge to our tools and an invitation to rethink the universe's hidden architecture. Now, shifting our gaze to another cosmic oddity, let's talk about the ultra-diffuse galaxies, or ghostly islands of stars that defy expectations. These galaxies are so faint, so thinly spread, that they're barely visible against the black canvas of space. Picture a city with its lights dimmed to near darkness, sprawling across an area the size of a metropolis but glowing with only a fraction of the brightness. That's the essence of a UDG. What's truly baffling isn't just their faintness, but the fact that they exist at all in the Perseus Cluster, a region of space where gravitational forces should tear such delicate structures apart. The Perseus Cluster is a cosmic battlefield where galaxies collide, merge, and are stripped of their gas by the cluster's intense gravity. In such a chaotic environment, fragile galaxies like UDGs shouldn't survive. Yet they do, scattered like delicate glass ornaments in a storm. How one theory suggests these galaxies are wrapped in cocoons of dark matter, their invisible halos acting like shields against the cluster's gravitational assaults. Dark matter's gravitational grip could be the only thing holding these wispy structures together, preventing them from being shredded by their more massive neighbors. But here's the twist: some UDGs seem to have surprisingly little dark matter, which throws yet another wrench into the mystery. If they're not held together by dark matter, what's keeping them intact? Could they be remnants of larger galaxies that were stripped down to their barest skeletons, leaving behind only their most resilient stars? Or are they failed galaxies, places where star formation never truly took off, leaving them as cosmic afterthoughts? The answers aren't clear, but each discovery pushes astronomers to rethink how galaxies form and endure in hostile environments. What makes UDGs even more intriguing is their size. Some span tens of thousands of light years, comparable to our Milky Way, yet contain less than 1% of its stars. Imagine a balloon stretched to the size of a beach ball but filled with only a whisper of air. That's the scale of their enigma. Their stars are so spread out that if you stood on a planet inside one, the night sky would appear almost empty, with only a few distant pinpricks of light breaking the darkness. The discovery of these ghostly galaxies has forced scientists to confront gaps in our understanding of galaxy evolution. Are UDGs rare flukes, or are they more common than we realize, hiding in plain sight because of their faintness? Telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope are peering deeper into clusters like Perseus, searching for more of these shadowy structures. Every new detection adds another piece to the puzzle, challenging assumptions and opening new questions. One thing is certain: ultra-diffuse galaxies are more than just cosmic curiosities. They're test cases for the laws of physics in extreme environments, offering clues about dark matter, galaxy formation, and the delicate balance of forces that shape the universe. Their very existence reminds us that even in the densest, most violent corners of space, nature finds ways to surprise us. And as we uncover more of these faint ghosts, we edge closer to understanding the full story of how galaxies, both bright and barely there, come to be. Now, as we dig deeper into the enigma of ultra-diffuse galaxies, let's explore one of the most compelling theories attempting to explain their existence: tidal stripping. Picture a massive galaxy, rich with stars and gas, drifting too close to the gravitational whirlpool of the Perseus Cluster. The cluster's overpowering tides begin to pull away the galaxy's outer layers, like an ocean current slowly eroding a coastline. Over billions of years, what remains is a ghostly, stripped-down version of its former self, barely holding onto its stars but still stretching across vast distances. Could this be how ultra-diffuse galaxies are born? This idea suggests that UDGs aren't failed galaxies at all, but rather the survivors of extreme cosmic violence. In the dense environment of the Perseus Cluster, galaxies frequently interact, collide, and tear each other apart. When a larger galaxy ventures too close to the cluster's core, tidal forces, the same kind that create the spectacular tales of interacting galaxies, could strip away its gas and most fragile stars, leaving behind only its dense, resilient core. The result, a faint, extended galaxy that somehow endures despite losing most of its material. But there's a catch. Some ultra-diffuse galaxies show signs of being rich in dark matter, while others appear to have very little. If tidal stripping were the sole explanation, we'd expect these galaxies to retain their dark matter halos, as dark matter is thought to be more resistant to stripping than visible matter. Yet, observations reveal a puzzling mix. Some UDGs align with this theory, their dark matter halos seemingly intact, while others defy it entirely, appearing almost devoid of dark matter. This inconsistency forces astronomers to ask, could there be multiple pathways to creating these ghostly galaxies? One possibility is that UDGs are cosmic chameleons, some born from the remnants of stripped galaxies, others from entirely different origins. For instance, a few might be failed galaxies where star formation simply never took off. Imagine a cloud of gas that never quite condensed enough to ignite a burst of stars, leaving behind a faint, sprawling structure. Alternatively, some could be the products of chaotic mergers, where the collision of smaller galaxies scattered stars in an unusually diffuse pattern. Adding another layer to the mystery, recent simulations suggest that tidal stripping doesn't always leave galaxies ultra-diffuse. Sometimes the process can compress a galaxy, making it more compact rather than more spread out. This raises the question, what specific conditions lead to the creation of UDGs rather than other remnant structures? The answer might lie in the delicate balance between a galaxy's initial mass, its trajectory through the cluster, and the timing of its interactions. What's clear is that ultra-diffuse galaxies, whether born from tidal forces or stunted growth, challenge our assumptions about how galaxies evolve. They force us to reconsider the role of environment in shaping galactic structures and the resilience or fragility of dark matter. Every new observation, whether from ground-based telescopes or cutting-edge space observatories, peels back another layer of this cosmic onion, revealing just how much we still have to learn. As we continue our journey through the Perseus Cluster's mysteries, these ghostly galaxies serve as a reminder that even the faintest, most overlooked corners of the universe hold profound secrets. Whether they're the stripped remnants of larger galaxies or cosmic underdogs that never quite thrived, UDGs are rewriting the story of galactic evolution, one wisp of starlight at a time. Now, shifting our gaze to another cosmic spectacle, let's unravel the mystery of galaxies hurtling through the Perseus Cluster at unimaginable speeds. These aren't just ordinary galaxies drifting with the cosmic flow. They're celestial renegades, ejected at velocities so extreme they defy conventional explanations. Picture a galaxy not just moving but catapulted across space as if slingshotted by some invisible titanic force. What could launch an entire galaxy into such a high-speed escape? One leading theory points to the gravitational tug-of-war between supermassive black holes. When galaxies merge, their central black holes spiral toward each other, eventually colliding in a cataclysmic event. But sometimes, instead of merging, the intense gravitational interaction can fling one of the black holes, and the galaxy hosting it outward at staggering speeds. Imagine a cosmic game of billiards where the energy of the collision sends one ball rocketing across the table. In this case, the ball is an entire galaxy, ejected at thousands of kilometers per second. Yet, there's a twist. Some of these high-speed galaxies show no signs of recent mergers or disrupted structures, leaving astronomers puzzled. If black hole interactions aren't the sole culprit, what else could be at play? Enter dark matter. The invisible scaffolding of the universe might hold the answer. Simulations suggest that dense clumps of dark matter could create gravitational kicks, propelling galaxies to extraordinary velocities. Think of it as stepping on a hidden ramp in the dark galaxies might be launched by unseen bumps in the cosmic terrain, but the plot thickens further. A few of these ejected galaxies appear to be stripped of their dark matter entirely, as if whatever force expelled them also ripped away their invisible halos. This raises a provocative question. Could dark matter itself be interacting in ways we don't yet understand? Some theories propose exotic dark matter particles that collide and scatter, transferring momentum to visible matter. Others speculate that these galaxies might be encountering regions where dark matter behaves unusually, like cosmic vortices that fling objects outward. Adding to the intrigue, the trajectories of these high-speed galaxies often don't align with the cluster's overall motion. Instead of following the expected flow of the Perseus Cluster's gravitational field, they dart off at odd angles as if pushed by a hand we can't see. This misalignment challenges our models of how gravity operates in clusters, suggesting that either our understanding of cluster dynamics is incomplete or that entirely new physics might be at work. What makes these ejections even more baffling is their rarity. Only a handful of such galaxies have been spotted in the Perseus Cluster, making them cosmic outliers. Are they the survivors of freak gravitational encounters, or do they hint at a larger population of high-speed galaxies we've yet to detect? The answer could lie in more sensitive surveys, capable of spotting these faint, fast-moving objects against the cluster's bright backdrop. As we piece together the puzzle of these galactic speedsters, one thing becomes clear: their existence forces us to rethink the extremes of cosmic violence. Whether launched by black holes, dark matter, or something even more exotic, these galaxies are a testament to the universe's capacity for chaos. Every new discovery peels back another layer, revealing just how dynamic and unpredictable the cosmos truly is. Now let's take a closer look at the gravitational slingshot effect and how it might be launching galaxies at breakneck speeds across the Perseus Cluster. Picture a playground swing, push it at just the right moment, and it soars higher with every pass. In space, gravity can pull off a similar trick. When a galaxy swings close to a supermassive black hole or a dense knot of dark matter, the gravitational pull can whip it away at incredible speeds. But here's the twist: not all these high-speed galaxies show the same scars, and that's where the debate heats up. On one side, we have the supermassive black hole theory. These cosmic behemoths lurking at the centers of galaxies pack enough gravitational punch to fling stars or even entire galaxies outward if they get too close. Imagine two black holes locked in a dance during a galaxy merger. As they spiral toward each other, their immense gravity can slingshot one of them into space, taking its host galaxy along for the ride. Astronomers call this a gravitational recoil, and it's like a cosmic version of a catapult. Some of the fastest ejected galaxies in the Perseus Cluster could be victims or beneficiaries of this violent process. Yet, not every high-speed galaxy fits this story. Some show no signs of recent mergers or the telltale distortions you'd expect from a black hole slingshot. That's where dark matter steps into the spotlight. Dark matter, the invisible glue holding galaxies together, might also be the unseen hand behind these ejections. Simulations suggest that dense clumps of dark matter could create gravitational hotspots. If a galaxy passes too close, it might get a kick, like a surfer catching a sudden wave propelling it to extreme speeds. Even stranger, some of these galaxies seem to have lost their dark matter halos entirely, as if the same force that ejected them also stripped them bare. Could dark matter be interacting with itself in ways we've never seen? The mystery deepens when we examine the trajectories of these galaxies. Many don't follow the expected paths dictated by the cluster's gravity. Instead, they veer off at odd angles as if nudged by something unseen. This misalignment hints that our current models of gravity might be missing a piece of the puzzle. Could there be exotic forms of dark matter, particles that collide and scatter, transferring energy to visible matter? Or perhaps regions where dark matter's pull behaves unexpectedly, like cosmic whirlpools flinging galaxies off course? What's truly fascinating is how rare these high-speed galaxies are. Only a handful have been spotted in the Perseus Cluster, making them cosmic anomalies. Are they the result of freak gravitational encounters, or do they represent a larger population we've yet to find? Future telescopes with sharper eyes and wider views might uncover more of these speedsters hiding in the cluster's glare. So, where does this leave us, whether it's black holes playing gravitational pinball or dark matter's hidden hand? These galactic ejections challenge our understanding of the universe's most fundamental forces. Every discovery peels back another layer, revealing just how wild and unpredictable the cosmos can be. And as we dig deeper, one thing becomes clear: the Perseus Cluster still has plenty of secrets left to share. Now, let's turn our attention to something even more unexpected: a cosmic hum echoing through the Perseus Cluster. Imagine standing in a vast, empty cathedral where the faintest whisper lingers for centuries. That's the kind of eerie phenomenon astronomers have detected here, but on a scale far grander. These aren't sound waves as we know them. Space is a near-perfect vacuum after all, but rather ripples of pressure moving through the superheated gas that fills the cluster. What's baffling is how these waves persist for billions of years, defying the laws of physics that say they should dissipate long before. The hum was first picked up by NASA's Chandra X-ray Observatory, which revealed subtle, rhythmic patterns in the cluster's gas. Think of it like the vibrations of a plucked guitar string, but one that never fades. These waves oscillate at frequencies millions of times lower than human hearing, creating a deep, cosmic drone. The leading theory suggests they're the aftermath of violent events, like supermassive black holes stirring the gas with their jets. But here's the puzzle: even the most energetic outburst shouldn't keep these waves alive for so long. It's as if the cluster has its own built-in amplifier, constantly reinforcing the signal. One possibility is that the gas itself is far more dynamic than we thought. Turbulence, magnetic fields, or even interactions with dark matter could be feeding energy back into the waves, preventing them from dying out. Some researchers speculate that the hum might be a relic of ancient cluster mergers, like the aftershocks of a colossal collision. If true, it would mean we're listening to a fossilized echo of the cluster's most violent era. But why haven't other clusters shown similar signatures? The Perseus Cluster seems to be singing a solo in a universe that's otherwise silent. Then there's the dark matter angle. Could these waves be evidence of dark matter particles interacting with the gas in ways we've never detected? It's a long shot, but if dark matter exerts even a tiny force on ordinary matter, it might leave behind these subtle imprints. Alternatively, the hum could hint at undiscovered physics, perhaps a previously unknown property of space-time or gas dynamics that only manifests in extreme environments like galaxy clusters. What makes this hum so intriguing is its sheer endurance. Most cosmic phenomena flare up and vanish in the blink of an eye, astronomically speaking. But these waves have outlasted galaxies, stars, even entire civilizations. They're a reminder that the universe operates on timescales we're only beginning to grasp. Future observatories like the Square Kilometre Array might finally decode this cosmic melody, revealing whether it's a random quirk or a profound clue about the fabric of space itself. For now, the hum remains one of the Perseus Cluster's most haunting mysteries. Whether it's a remnant of ancient violence, a whisper from dark matter, or something entirely new, it challenges us to listen more closely to the universe's hidden soundtrack. And as we tune in, we might just discover that space isn't as silent as we once believed. Now, shifting our focus deeper into this cosmic hum, let's explore the tantalizing idea that these waves might be resonating with secrets buried in the cluster's past, or even whispers from the invisible grip of dark matter. The persistence of these pressure ripples raises a critical question. Are we hearing the distant echoes of ancient mergers, or could this be evidence of dark matter's subtle hand at work? Both possibilities stretch our understanding of physics in thrilling ways. Take the merger theory first. Galaxy clusters like Perseus are products of violent collisions, cosmic pile-ups where smaller clusters smash together over billions of years. These events release unimaginable energy like boulders dropped into a pond, sending shockwaves through the surrounding gas. Normally, such ripples would fade as the gas absorbs their energy. But in Perseus, they've endured, almost as if the cluster itself is ringing like a bell. One explanation is that the mergers were so colossal, their vibrations became trapped in the gas, bouncing between regions of differing density. Picture sound waves in a canyon where the geometry keeps echoes alive far longer than in open air. If the cluster's gas is structured just right, it could act as a natural resonator, preserving these waves far beyond their expected lifespan. But here's where it gets stranger. For the waves to last this long, the gas would need to be remarkably undisturbed, no major turbulence, no recent mergers to disrupt the rhythm. Yet the Perseus cluster is anything but quiet. Its central supermassive black hole, NGC 1275, frequently erupts with jets that churn the gas like a spoon in soup. So how do the waves survive this chaos? Some theorists suggest the black hole's outbursts might actually fuel the resonance, pumping energy back into the waves at just the right frequency to sustain them. It's a delicate balance, like a singer hitting a note that makes a wineglass hum. If true, it would mean the cluster's hum isn't just a relic, it's a living phenomenon maintained by an ongoing cosmic dance. Then there's the dark matter angle. We know dark matter outweighs ordinary matter in the cluster by a factor of 5 to 1. Could its gravitational pull be subtly shaping these waves? Some models propose that dark matter's invisible halos around galaxies might nudge the gas in ways we can't directly see, creating faint ripples that amplify over time. Even more radical is the idea that dark matter particles themselves could interact weakly with the gas, transferring energy like a ghostly hand brushing against a curtain. These interactions would be infinitesimally small, but over billions of years, they might leave traces in the form of these unexplained waves. Of course, the challenge is testing these ideas. Current telescopes lack the sensitivity to map the hum's finer details, but next-generation instruments like the Square Kilometre Array could change that. By pinpointing the waves' exact frequencies and how they vary across the cluster, we might finally distinguish between merger echoes and dark matter's signature. Until then, the hum remains a cosmic riddle, one that reminds us how much we don't know about the forces shaping the universe's largest structures. What's certain is that this isn't just background noise. Whether it's a fossilized echo or a dark matter clue, the Perseus cluster's hum challenges us to rethink the rules of physics on scales we're only beginning to comprehend. And as we listen more closely, we might find that the universe's quietest sounds hold its loudest secrets. Now, turning our attention to another enigma hiding in the Perseus cluster, we encounter the puzzle of the missing baryons. This isn't some cosmic magic trick, it's a fundamental gap in our understanding of the universe's building blocks. According to measurements from the cosmic microwave background, the afterglow of the Big Bang, there should be a specific amount of ordinary matter, protons, neutrons, and electrons floating around in the cosmos. Yet when astronomers tally up all the visible gas, stars, and dust in the Perseus cluster, the numbers just don't add up. Nearly half of the expected ordinary matter seems to have vanished without a trace. So where did it go? One leading theory suggests these baryons aren't missing at all, they're just incredibly hard to detect. Imagine trying to find a single flashlight in a foggy forest. The fog scatters the light, making it nearly invisible from a distance. Similarly, the missing baryons might be hiding in a diffuse, superheated form known as the warm-hot intergalactic medium. This thin, invisible soup of ionized gas fills the spaces between galaxies, too hot to emit visible light but too cool to stand out in X-ray telescopes. In the Perseus Cluster, this gas could be threaded through its vast web-like structure, blending into the background like cosmic static. But even accounting for this elusive gas, the math still leaves room for mystery. Some researchers propose that another portion of the missing matter might be tied up in ultra-dense molecular clouds, cold, compact pockets of gas that evade detection because they don't emit much radiation. These shadows of the cosmic inventory could be lurking undetected, like icebergs beneath the surface of the cluster's brighter emissions. Alternatively, there's the possibility that some baryons have been pushed out of the cluster entirely, ejected by violent galactic winds or the shock waves of ancient collisions. The stakes here are high because baryons aren't just cosmic placeholders, they're the raw material for everything we see, from stars to planets to life itself. If we can't account for them, it hints at gaps in our models of how matter behaves in the most extreme environments. Next-generation telescopes, like the upcoming Athena X-ray Observatory, aim to hunt down these hidden reservoirs with unprecedented sensitivity. By mapping the faint glow of the warm, hot intergalactic medium or pinpointing the whispers of cold molecular clouds, we might finally close this cosmic ledger. What makes this phenomenon so compelling is its universality. The missing baryon problem isn't unique to Perseus. It's a puzzle repeated across the cosmos, suggesting a fundamental blind spot in how we observe or understand ordinary matter. Whether the answer lies in overlooked gas, exotic states of matter, or something entirely unexpected, solving it could rewrite our playbook for the universe's structure. For now, these vanished baryons remain one of the most persistent and humbling reminders that even the familiar ingredients of reality can still surprise us. Now, let's peel back another layer of this cosmic mystery by exploring where exactly these elusive baryons could be hiding. While we've touched on the warm, hot intergalactic medium, there's more to this story. Like a detective piecing together clues, astronomers have identified several potential hiding spots for the missing matter, each with its own unique challenges for detection. One of the most promising candidates is the vast spiderweb-like network of filaments that connect galaxies across the universe. These filaments, made of the same warm, hot intergalactic medium, act as cosmic highways for gas, threading through the voids between clusters. The gas here is so hot millions of degrees that it's ionized, meaning its atoms have been stripped of electrons. This makes it incredibly faint in visible light but detectable in X-rays. However, even our best X-ray telescopes struggle to map its full extent because the signal is drowned out by brighter sources, like the Perseus Cluster's own glowing core. It's like trying to hear a whisper at a rock concert, but there's another twist. Some of the missing baryons might be lurking in colder, denser forms, specifically in molecular clouds. These are frigid pockets of gas, rich in molecules like hydrogen and carbon monoxide, which don't emit much light or heat. They're the cosmic equivalent of black ice on a road, nearly invisible until you're right on top of them. In the Perseus Cluster, such clouds could be scattered between galaxies, camouflaged by the cluster's own radiance. Detecting them requires specialized instruments, like radio telescopes tuned to the faint signals these molecules emit. Yet, even then, many could remain hidden if they're too diffuse or shielded by dust. Then there's the possibility that some baryons have been ejected entirely from the cluster's grasp. Galactic winds, driven by supernova explosions or supermassive black hole activity, can blast gas out into intergalactic space at incredible speeds. Over billions of years, this expelled material might drift too far to be associated with the cluster anymore, effectively vanishing from our cosmic senses. Similarly, violent collisions between galaxies within the cluster could have flung gas outward, dispersing it so thinly that it's now undetectable with current technology. What's fascinating is that these hidden reservoirs aren't just theoretical. They've been glimpsed in other parts of the universe. For example, observations of distant quasars have revealed absorption lines in their light caused by ionized gas along the line of sight. These serve as breadcrumbs hinting at the warm-hot intergalactic medium's presence. Meanwhile, surveys of nearby galaxy clusters have occasionally spotted faint molecular clouds, though never in the quantities needed to solve the missing baryon problem outright. The challenge lies in bridging the gap between these scattered hints and a complete picture. Future telescopes like the European Space Agency's Athena mission promise to revolutionize this search. With sensitivity far beyond current X-ray observatories, Athena could map the warm-hot intergalactic medium in unprecedented detail, while next-generation radio arrays might finally uncover those elusive cold clouds. Until then, the missing baryons remain a testament to the universe's knack for keeping secrets, and a reminder that even the most ordinary ingredients of the cosmos can defy our expectations. So while we don't yet have all the answers, each theory brings us closer to understanding where the universe stashes its ordinary matter. Whether it's hidden in plain sight or scattered beyond our current reach, solving this puzzle won't just fill a gap in our equations, it'll reveal new chapters in the story of how galaxies and clusters evolve. And that's what makes the hunt for these missing baryons so thrilling. Moving from the hunt for missing baryons, let's turn our attention to another enigma, the peculiar clumping of hot gas in the Perseus Cluster. If you imagine a cluster's gas as a smooth, evenly spread soup, the Perseus Cluster throws that assumption out the window. Instead, its gas is lumpy, uneven, and full of surprises, defying the tidy models astronomers once relied on. At the heart of this puzzle is the behavior of the intracluster medium, the superheated gas that fills the space between galaxies. Theory suggests that over time, this gas should settle into a relatively uniform distribution, like cream mixing into coffee. But in Perseus, it's more like lumps of dough in a poorly stirred batter. Some regions are dense and fiery, while others are bizarrely sparse. What's causing this patchwork? One leading suspect is the cluster's violent history. Perseus didn't grow peacefully. It devoured smaller galaxy groups in a series of cosmic collisions. These mergers send shockwaves through the gas, creating turbulence that can linger for billions of years. Think of it as dropping a rock into a pond, but instead of smooth ripples, you get chaotic splashes that refuse to settle. Observations back this up. X-ray maps show twisted, asymmetric patterns in the gas, hinting at past upheavals. Yet, even accounting for mergers, the gas clumps more than simulations predict. Then there's the role of magnetic fields. While invisible to the naked eye, these forces can shape gas like an unseen hand. In Perseus, magnetic fields may be trapping pockets of gas, preventing them from spreading evenly. It's similar to how Earth's magnetic field corrals charged particles into the Van Allen belts. But in the cluster, the fields are far stronger and messier, possibly sculpting the gas into the odd configurations we see. But here's the twist. Some clumps are too dense and cool to fit the merger or magnetic field explanations. These blobs, rich in heavier elements like iron, suggest something else is at play. One theory points to sloshing, where the cluster's central galaxy wobbles like a spoon in a cup, churning the gas. Another wild idea involves dark matter's gravitational influence creating invisible wells that trap the gas. Neither fully solves the mystery, leaving astronomers scratching their heads. What makes this phenomenon so crucial is its ripple effect. Uneven gas distribution impacts how we measure the cluster's mass, its evolution, and even the growth of galaxies within it. If our models can't explain Perseus's gas, how reliable are they for other clusters? Future missions like Japan's X-RISM satellite aim to study these gas patterns in finer detail, potentially unlocking new physics. Until then, the Perseus Cluster's lumpy gas remains a reminder that the universe loves to defy our expectations, one uneven clump at a time. This isn't just about gas, it's about understanding the forces that shape the cosmos. Every irregularity challenges us to rethink the rules, and that's where the real discovery begins. But what if the violent history of the Perseus Cluster isn't the whole story? While mergers can explain some of its chaotic gas distribution, they don't account for everything. Let's dig deeper into the clues left behind by these cosmic collisions and see where the puzzle pieces still don't fit. Take the cluster's so-called cold fronts, sharp edges in the gas where temperatures drop abruptly. These are like cosmic battle scars, marking where smaller clusters or galaxy groups plowed into Perseus. Simulations show these collisions should create turbulence, but what's strange is how long these features persist. Some cold fronts appear pristine, as if frozen in time for billions of years, defying expectations that they'd blur and fade. It's like finding a perfectly preserved footprint in mud that should have washed away ages ago. Then there's the problem of scale. While mergers can stir up gas, the unevenness in Perseus spans distances much larger than typical collision debris. Some gas clumps are hundreds of thousands of light years across, far bigger than what most merger models predict. Imagine stirring a pot and finding not just small bubbles, but massive, unmixed globs floating stubbornly in the broth. The timing doesn't always add up either. Certain gas patterns suggest past mergers occurred at odd angles or speeds, leaving behind structures that don't match any straightforward scenario. One leading theory proposes a double merger, two separate collisions happening in quick succession, like cars hitting the same patch of ice from different directions. Yet even this can't explain why some gas pockets are richer in heavy elements, as if they were cooked in separate cosmic kitchens before being tossed into the mix. And here's the real kicker. Some of the most perplexing gas clumps are found near the cluster's center, where the supermassive black hole in NGC 1275 lurks. Could its outbursts be adding to the chaos? Black holes are known to blow bubbles of energy into their surroundings, but the scale of disturbance needed to create these gas anomalies would require energy levels beyond what we've observed. It's like a fan stirring a hurricane. The math just doesn't balance. This leaves astronomers with a tantalizing possibility. Maybe dark matter is pulling invisible strings. The gravitational tug of unseen dark matter could be sculpting the gas in ways we don't yet understand, creating pockets where gas collects or gets stretched thin. If true, studying Perseus's lumpy gas might be one of our best windows into the hidden architecture of the cosmos. So while mergers explain part of the mystery, the full picture remains blurry. Each clue, whether it's the enduring cold fronts, the oversized clumps, or the black hole's potential role, points to forces we're still unraveling. The Perseus Cluster isn't just a snapshot of violence. It's a cosmic crime scene where the usual suspects don't cover all the evidence. And that's what makes it so thrilling, because every unanswered question is a chance to rewrite the rules. Now, let's turn our attention to another cosmic oddity hiding in the heart of the Perseus Cluster, the curious case of the too many red giants. Nestled in the cluster's central galaxies, astronomers have spotted an unexpected overabundance of these aging stars, glowing like embers in the cosmic dark. Red giants are typically the final act for sun-like stars, puffing up as they exhaust their fuel. But here's the puzzle: there shouldn't be this many of them in one place. It's like walking into a retirement home and finding it packed with residents who all turned 100 in the same year. Statistically, something doesn't add up. So what's going on? One leading idea ties back to the cluster's violent environment. The Perseus Cluster is a gravitational pressure cooker where galaxies jostle and merge, stripping gas and disrupting star formation. In most galaxies, this would leave behind a mix of stars of different ages. But in Perseus, it seems the chaos might have triggered a synchronized baby boom of stars billions of years ago, which are now reaching their red giant phase together. Think of it like a forest where all the trees were planted at once. Now they're all shedding leaves at the same time, yet there's a wrinkle in this theory. If a burst of star formation happened long ago, we'd expect to see other traces, like an excess of white dwarfs, the corpses of stars that have already burned out. But those are curiously scarce. This mismatch has led some researchers to propose that the red giants might be immigrants, captured from smaller galaxies that fell into the cluster and were torn apart. Picture a bustling city where newcomers from rural towns skew the demographics, except here, the city is a galaxy and the newcomers are stars dumped by gravitational forces. Then there's the wild card: could the cluster's supermassive black hole be involved? The intense radiation and winds from NGC 1275 might have altered how stars aged in its vicinity, either delaying or accelerating their evolution in ways we don't fully understand. It's as if a cosmic caretaker selectively pruned the stellar population, leaving behind an unnatural abundance of red giants. But perhaps the most tantalizing possibility is that we're seeing a flaw in our models of stellar evolution itself. The physics of how stars age, especially in extreme environments like galaxy clusters, might need rewriting. If true, Perseus's red giants aren't just a local oddity, they're a clue that the universe has more tricks up its sleeve than we thought. What's clear is that this overabundance isn't just a counting error. It's a signpost pointing to deeper mysteries about how stars live, die, and congregate in the universe's most crowded neighborhoods. And like so much in the Perseus Cluster, it leaves us with more questions than answers, questions that could reshape our understanding of stellar life cycles altogether. Now, shifting our gaze deeper into this cosmic puzzle, let's consider the possibility that the Perseus Cluster's extreme environment might have rewritten the rules of star formation altogether. Imagine a place where gravity's tug of war and searing gas clouds collide, a realm so chaotic it could twist the life cycles of stars into something unrecognizable. One compelling angle is the cluster's history of galaxy collisions. When galaxies merge, their gas clouds slam together, often igniting frenzied bursts of new stars. But in Perseus, these bursts might have been oddly synchronized, like a symphony where every instrument hits the same note at once. If countless galaxies merged in rapid succession billions of years ago, they could have produced a generation of stars that all reached old age simultaneously, explaining today's red giant surplus. Yet, as we saw earlier, the missing white dwarfs complicate this picture. It's like finding a photo of a packed concert but no evidence of the crowd ever leaving. Where did everyone go? Then there's the role of the cluster's scorching intergalactic gas. Temperatures here can reach tens of millions of degrees, hot enough to strip raw star-forming material from galaxies as they plow through. In such a hostile environment, star formation might have been cut short, leaving behind a skewed population where only certain stars, like red giants, manage to thrive. Think of it as a garden where frost kills most seedlings, but a handful of hardy plants survive to dominate. Intriguingly, the cluster's central galaxy, NGC 1275, adds another layer of mystery. Its supermassive black hole spews jets of energy that could have reheated nearby gas, temporarily pausing star formation and creating a gap in the stellar record. Later, when conditions cooled, a delayed wave of stars might have emerged, now aging in unison. This would be like pressing pause on a song, then restarting it only to hear every instrument playing the same delayed beat. But the boldest theory challenges our very understanding of how stars evolve. Normally, a star's fate depends on its mass. Heavier stars burn out fast, while lighter ones simmer for eons. Yet in Perseus, something might have altered this script, perhaps intense radiation or magnetic fields stretching across the cluster, effectively stretching some stars' lives or hastening others' demise. If true, it's as if the universe quietly rewrote the rules of stellar retirement, and we're only now noticing the discrepancies. What makes this enigma so gripping is its ripple effect. If Perseus's red giants defy conventional models, other clusters might hold similar surprises, forcing us to rethink how stars behave in the universe's densest neighborhoods. For now, these aging stars remain cosmic outliers whispering clues about the untold stories of star formation, waiting to be deciphered. Now, turning our attention to another cosmic oddity, we encounter the perplexing case of IC 310, a galaxy that refuses to play by the rules. Nestled within the Perseus Cluster, IC 310 is no ordinary neighbor. What sets it apart is its supermassive black hole, which behaves more like a capricious cosmic fireworks display than the predictable engine we'd expect at the heart of an active galaxy. Most supermassive black holes in active galactic nuclei, or AN, follow a relatively steady pattern. They consume surrounding material, heating it to extreme temperatures and emitting radiation across the spectrum, often in predictable bursts. But IC 310 black hole is different. It produces sudden, erratic gamma-ray flares, some of the most energetic light in the universe, and they appear without warning. Imagine flipping a light switch and getting a blinding strobe instead of a steady glow. That's the kind of unpredictability we're dealing with here. These gamma-ray outbursts are so intense and brief that they challenge our understanding of how black holes accelerate particles. Normally, the jets streaming from a black hole's poles act like cosmic particle colliders, hurling matter outward at nearly the speed of light. Yet IC 310 flares suggest something far more violent and chaotic is at work. One theory proposes that the black hole's magnetic fields are snapping and reconnecting, like rubber bands stretched to their limit, releasing enormous bursts of energy in the process. Another idea is that the black hole's accretion disk, the swirling ring of doomed matter, is fragmented, causing erratic feeding frenzies that spark these extreme flares. Adding to the mystery, IC 310 flares don't match the behavior of other known gamma-ray sources, such as pulsars or blazars. Pulsars rotate with clockwork precision, and blazars have jets pointed almost directly at us, creating a steady stream of light. IC 310, however, seems to flicker on and off like a malfunctioning beacon, as if its black hole is toggling between states of activity faster than our models can explain. What makes IC 310 particularly fascinating is the sheer scale of its emissions. During one observed flare, it became one of the brightest gamma-ray sources in the sky for just a few hours. This kind of volatility suggests that the processes at work here operate on timescales far shorter than anything we've seen elsewhere. It's like catching a lightning strike in slow motion, only to realize the bolt changed direction mid-flight. The implications ripple outward. If IC 310 black hole is breaking the rules, others might be too. We just haven't noticed yet. This galaxy forces us to reconsider how black holes convert energy into light and whether our current AGN models are missing a critical piece of the puzzle. For now, IC 310 stands as a cosmic rebel, defying expectations and reminding us that even in the vastness of space, the universe still has a few surprises up its sleeve. Now, let's take a closer look at the engine behind IC 310's bizarre behavior. The particle acceleration happening near its supermassive black hole. This isn't just a case of cosmic chaos, it's a laboratory for extreme physics, pushing the limits of what we thought possible. Black holes are famous for their gravitational pull, but their surroundings are also some of the most efficient particle accelerators in the universe. Normally, particles get a predictable boost as they spiral toward the event horizon, funneled into jets that shoot out at nearly the speed of light. These jets are like cosmic highways where particles gain energy over vast distances. But IC 310 black hole seems to have a shortcut, or maybe even a different rulebook altogether. The gamma-ray flares we see from IC 310 suggest particles are being accelerated to mind-bending energies in a fraction of the time it should take. Picture this: if a typical black hole jet is a marathon runner building speed gradually, IC 310 version is more like a sprinter exploding off the starting blocks. The flares are so brief and intense that they hint at an acceleration process operating on scales far smaller than we've ever observed. One leading idea is magnetic reconnection, a process where magnetic field lines snap and realign, releasing enormous bursts of energy. On Earth, we see this in solar flares, but in IC 310, the scale is unimaginably larger, with magnetic fields packing enough punch to hurl particles to near-light speeds in moments. Then there's the wild card, turbulence. The environment around IC 310 black hole might be so violently chaotic that particles are getting whipped around like leaves in a hurricane, gaining energy through countless collisions and shocks. If true, this would challenge our models of how particles behave in such extreme conditions. Normally, we expect some order in the chaos, a rough pattern to the madness, but IC 310 flares suggest the turbulence here operates on another level entirely. What's especially puzzling is how these particles reach such extreme energies without simply tearing themselves apart. The laws of physics place limits on how quickly particles can accelerate before radiation losses sap their energy. Yet somehow, IC 310 particles are breaking through that barrier, reaching energies that should be impossible under standard theories. This has led some researchers to speculate about unknown physical processes, perhaps even interactions involving dark matter or exotic particles we haven't yet discovered. IC 310 forces us to rethink the playbook for particle acceleration. If its black hole can do this, others might too. We just haven't caught them in the act yet. Every flare from this galactic rebel is a clue, a piece of a puzzle that could rewrite our understanding of how the universe's most powerful engines work. And as we keep watching, one thing is certain: IC 310 isn't done surprising us. What an incredible journey through the cosmic oddities of the Perseus Cluster we've had. From the missing mass problem that hints at the elusive nature of dark matter, to the ghostly filaments stretching across the void, and the baffling particle acceleration near IC 310 black hole, each mystery peels back another layer of how little we truly understand about the universe. This cluster isn't just a collection of galaxies, it's a cosmic puzzle box challenging the very foundations of physics and cosmology. Think about it. The Perseus Cluster defies expectations at every turn. Its radio halos, X-ray cavities, and ultra-diffuse galaxies don't just bend the rules, they seem to rewrite them. Even the cold fronts, stable for billions of years, and the eerie hum resonating through its gas clouds, force us to question whether we're missing something fundamental about how the cosmos operates. And let's not forget the dark galaxy, a cosmic phantom that might be made almost entirely of dark matter, or the way NGC 1275 shines far brighter than it should. Every discovery here pulls us deeper into the unknown, but that's what makes this so thrilling. Each unexplained phenomenon isn't just a gap in our knowledge, it's a door to new physics, a clue waiting to be deciphered. The Perseus Cluster is more than a scientific curiosity. It's a reminder that the universe is stranger, wilder, and more mysterious than we ever imagined. And with every telescope pointed its way, with every new observation, we get a little closer to unraveling these enigmas. So, what's your favorite mystery from the Perseus Cluster? Is it the missing baryons, the high-speed galaxy ejections, or something else entirely? Drop your thoughts in the comments. I'd love to hear which cosmic puzzle fascinates you the most. And if you're as captivated by deep space mysteries as I am, don't forget to subscribe and hit the notification bell. There's always more to explore, more questions to ask, and more wonders waiting in the vast unknown. The universe isn't done surprising us, and neither are we. Let's keep searching together.